we took the sample and looked at it under the optical microscope at some of the points that we just did measurements on to see what was going on. So this is one of the spots. These are two smaller spots off to the side. This is under AFM. And this is actually the physical topology. And this is SEM. So this is scanning electron microscopy. And so what you can see here is that there's an amorphous region and then crystallites that are forming on the surface. So these crystallites, so these are actually the crystallites of the selenium from within the material. And so it turns out that if I use different powers of the Raman laser to measure this, I can get different thresholds for this peak to start to appear at different temperatures. If I plot these thresholds with the temperature at which they appear, I can plot a line such that I get back what the temperature would be to induce selenium migration from within the material to the surface if I did not use optical heating as well. And that turns out to be 440 Kelvin. Okay, so this is very important if you're trying to make any devices with this material and you need to cure it for something. Okay, another thing we did is I switched Raman lasers and used the red laser, and I performed measurements on titanium diselenide, copper-doped titanium diselenide with various copper dopings from room temperature down to roughly 88 Kelvin. And this allowed me to fill out a large portion of the phase diagram. So what you're seeing here is pure increased copper doping, where this right here is the one just beyond the when you induce superconductivity at lower temperatures, and this is even further beyond that. So there are three particular results that come about from doing this experiment. The first one is, if you look here, this A1G peak, as you dope with copper, it splits. And so if you fit this splitting with two Gaussian curves and then plot them, and so what I'm showing you here is the difference in energy between these two Gaussian peaks, and the blue curve is the difference in height, the ratio of their height. And you can see that at 0.04 is when the splitting starts to come in. Now it turns out that we're using X-ray measurements. So with these X-ray measurements, we can monitor the superlattice peak and the normal lattice peak. So the superlattice peak is the red curve, and the normal lattice peak is the blue curve. That for titanium diselenide, so for pure titanium diselenide, these are commensurate with each other. They're locked in place. The superlattice is an integer multiple. It's the reverse of that. Sorry. The normal lattice is an integer multiple of the superlattice, and so these systems are highly coupled. But as you dope the material with copper, the superlattice peak broadens and it starts to become misaligned with the normal lattice peak. And as you continue to dope it with copper, this misalignment becomes larger and larger. This incommensuration is what this is called, becomes larger and larger. And this is shown in the phase diagram here, where if we do the same experiment that I showed you with the neutron diffraction scattering, where we find the transition temperature, we find out that rather than just the commensurate charge density wave phase here, there's also an incommensurate charge density wave phase that coexists with superconductivity at low temperatures. So the incommensuration that I was talking about is like so. So this is what a commensurate lattice would look like, and this is what an incommensurate lattice look like. And the difference between these is the incommensuration. And you can see that again, I would have to go to higher and higher order peaks. So the second result that comes from this is when we look at this EG mode right here. So the EG mode is the shearing mode, like I said before, and if I show you this phonon band diagram with the soft phonon right here, if I trace that back to gamma, I'm going to be monitoring this peak right here, and it turns out that this peak hardens in energy, increases in energy as I go through the phase transition, and then lowers in energy again afterwards as I go lower. And so these blue dots are the pure kit for the pure titanium diselenide. For 0.004, this is the green dots, the green dots, and then 0.026, and then 0.046. And so this tracks the suppression of the transition temperature. Another, and the last result, this is a very important one, is these superlattice peaks right here. These superlattice peaks I get in the Raman spectra when I go below the phase transition temperature. And so that's obvious, that's what's seen here. But if I dope it with copper and I look at this particular picture right here, something's interesting is happening. The background is decreasing with lower temperature, as it should with Raman spectra. But the background over here is not decreasing with lower temperature. In fact, and this is the region where I would be seeing superlattice peaks at lower temperature, below the phase transition. But since this is copper X equals 0.07, this is in the part of the phase diagram that I cannot access the charge density wave with liquid nitrogen temperatures. If I keep doping with copper, this background behaves as it should, just like this background does. And so if I take a difference between these 2 points and make a heat map with this, I get the following phase diagram, where the blue triangles denote the charge density wave transition temperature from the EG phonon modes, and the heat map that you're seeing here is the fluctuations above the phase transition temperature that I showed you just in the previous slide. And so these fluctuations extend about 100 Kelvin above the phase transition temperature and terminate at roughly, get strongly reduced at roughly 0.08, X equals 0.08, which is ideal copper doping for the superconducting phase at much lower temperatures. But keep in mind that this phase diagram only goes down to 100 Kelvin, so that means that the experiments only go down to around here. And so we modify the phase diagram like so, with this piece of information. The next experiment that I did was with transient optical spectroscopy of titanium diselenide. So in this experiment, this is ultrafast spectroscopy, so this is doing measurements with light at resolutions of 30 femtoseconds, so 10 to the minus 15 seconds, which is much faster than the time it takes for a molecule to oscillate. So what happens in this experiment is that a pump pulse excites electrons in the material, so that's the pump pulse of this pump path, and a probe pulse measures the excited state and the not excited state. So every other pulse, the pump is blocked and the probe is allowed to measure. So the probe effectively measures the equilibrium state of the material and the out of equilibrium state of the material. And since this is an optical reflectivity, what you can do is you can put this probe on a delay track and extend this time relative to the pump and get the exponential decay of the internal degrees of freedom of the system through these optical measurements. So this looks like this. This is a picosecond timescale on the vertical axis, and this is wavelength. And so this is what these measurements would look like, where the pump pulse hits the material at time 0, and the probe pulse measures it subsequently with the future measurements. Okay, so to give you an idea of the physics that's going on inside of the system when this happens, I'm going to show you some transient ARPAS measurements made by Rauer et al. And what I want you to keep in mind as I go through this is that the time constant of the exponential decay, which I'll explain in a moment, determines which mechanism is being monitored. So if I have the occupied electronic orbitals and an optical pulse pumps electrons above the Fermi energy, then this is the new distribution of atoms. This is the distribution of excited electrons. So this is at the time of the pump pulse. This is a couple of femtoseconds after the pump pulse, but just a few. And then this is when electrons thermalize with each other. So electron-electron interactions cause the electrons to scatter and adopt this distribution. And then electron-phonon interactions occur, which is the electrons thermalizing with the lattice. And so the distribution of the excited carriers sinks down further. And then electron-hole recombination occurs, where the excited electrons annihilate with the excited holes that are in the valence band, and you get something like toward true equilibrium. Okay, so this is actually a movie. So this is at a time before the pump pulse. And so right now, this is going to go into time 0, where you can see the electron density increasing up here. So this dark brown region is going to be more shaded. And so this is the renormalization of the band structure. This is still at 2 femtoseconds, and then slightly increasing at later and later times. And these electron states go from excited back to their equilibrium positions as you go to longer and longer time scales. And so one of the things I want to emphasize is that picosecond timescales are when electron-phonon interactions occur. So that's when you can get at that mechanism. Nanosecond timescales are when electron-hole recombinations occur. So that's when you can get at those particular mechanisms. Okay, so this is connected to my measurements like so. This is a before. This is a snapshot before the pump pulse, and this is a snapshot after the pump pulse. This is the difference between the two, where this is the extra electrons and this is the extra holes. So if we were to draw a box around these, then we could average all of the excited electrons or the excited holes through time to get something like this. where the blue is the excited holes and the red is the excited electrons. Now, this is done with a transient ARPUS measurement, but my measurements are transient optical, so what I actually monitor is I monitor the resonances between these electronic bands. So if they're monitoring this directly, I'm monitoring it through this 500 nanometer pulse right here, probe pulse right here. And this part of the band structure I'm monitoring through the 620 nanometer pulse. And so that gives you context for what these pictures look like. So this is at room temperature. This right here is the wavelength that monitors the SE4P valence band at the gamma point. So this is 620. And this is the TI3D conduction band monitoring the conduction band at the L point. And so this is at lower, much reduced temperatures. So this is 3 Kelvin in the charge density wave phase. And this is the signature of the new electronic band structure. So this is the folded SE4B valence band at 550 and 690 nanometers. Another way of making sure that you're convinced of this assignment is that I can take, if you look very closely, you can see, and it's hard to see with these graphs, but there are oscillations on top of these exponential decays. So here's the exponential decay, like I was talking about, and then there's these oscillations that you can see. If I do a Fourier transform of these transient spectra, I get out something like this. And so this right here is 3.4 terahertz, and it's localized at this place and the transient optical spectra. And so this is the oscillation associated with the charge density wave lattice. So, and this oscillation right here is a 6.2 terahertz oscillation, and it's localized here and here, here and here. And this is the normal lattice oscillations. And so so this is taken with a very low fluence pump pulse, so I don't perturb the system very much. But if I use a very high pump pulse and I melt the system, then I can eliminate the charge density wave lattice and just get the normal lattice frequencies back. And so this is a much more even more convincing of these assignments. And as far as physically what's going on with these oscillations, you have the optical pulse, which you excite, and if you excite with a pulse that has a faster time resolution than the oscillations that you're looking for, what's going to happen is these electronic bands that you leave behind are going to oscillate up and down in energy. And that's the oscillations that we're monitoring when we see these oscillations on the band structure. Okay. Oop. So what we do now is we take the experimental data, and we fit it with this equation. So this equation is the change in optical density, and it has in it an exponential decay function, so with a decay time, which is convoluted with an instrument response function, which is just a Gaussian that is at time 0, which physically means where the pump and the probe are overlapping. And then this is multiplied by a decay associate spectra. So a decay associate spectra, as the name implies, is an optical spectra associated with a particular exponential decay. So what this looks like is, and what you want to think about this as, the amplitude of the difference in optical density at each wavelength for the exponential decay. So this is just like the amplitude of the exponential decay for each wavelength. And so at room temperature, this is the normal phase response, so this red curve, and then this blue curve is at 3 Kelvin, and this is the charge density wave phase. Here's the 550 and the 690 nanometer optical signature of the charge density wave. And this is also the decay associate spectra for the nanosecond decay at different temperatures. So with this information in mind, there's an experiment where I use low fluence measurements for pure titanium diselenide. So this is the picosecond decay associate spectra, and this is for the nanosecond. If I do very low fluence measurements at multiple temperatures and make a heat map with it, this is the folded SE4P valence band. This is also the signature for that as well. But if you notice that at the phase transition temperature at 200, you still see optical signatures of the CDW phase, even much above the phase transition temperature. So what I'm doing is monitoring this part of the phase diagram, and I'm confirming with the other measurements that these are in fact fluctuations of the charge density wave. This is monitoring it through the electronic system before I was monitoring it through the phonon system. Another measurement that was done was on chirality symmetry breaking in titanium diselenide. So chirality, a very simple object to know what a chiral object is just your hands. You cannot superimpose your left hand onto your right hand just by any rotation. You have to use some mirror plane. And so in titanium diselenide, this was also found to be true with STM measurements. And so this is an STM of the surface. This is a domain that is let's say that's right-handed, and this is a domain that's left-handed. And in this domain, what they did was they found that the superlattice peaks decreased in amplitude as you rotated clockwise as you rotated clockwise in the inverse space. Whereas in the left-handed domain, the opposite is true, and this is shown here in these plots. And so what is going on here, the reason why they're decreasing as you turn clockwise or counterclockwise, is that the CDW vectors actually change direction as you go into the material. So here it's going to be red, green, blue, and here it's going to be red, blue, green. And that's the left-handed and the right-handed domains. So that's all well and good as a measurement of chirality in titanium diselenide, but it's only a measurement of the surface. And so if you want to demonstrate bulk chirality of the system, you can do circular dichroism measurements, which is an optical measurement. And so what you do is you take circularly polarized light, you send an equal amount of circularly polarized light, left-handed and right-handed, and that impinges on the material, an octavely active material, and it will preferentially absorb either left-handed or right-handed light, depending on the chirality of the system. So if it's a left-handed system, it will absorb one. If it's a right-handed system, it will absorb another. And mathematically, this is represented by the following equation. A CD signal is given by the imaginary part of an electric dipole transition vector. So that's this vector right here, dotted with a magnetic dipole vector. So what you want to think of that as is the electric dipole vector gives you the forward motion, whereas the magnetic dipole vector gives you the circular motion. If they're coupled together, then you're going to get the spiral motion, and that could be either left or right-handed. And so in our system, in titanium diselenide, you're not dealing with a system with magnetic dipoles, you're dealing with just electric dipoles. And so this can be expanded such that you induce a magnetic moment by virtue of two coupled electric dipole moments that are separated by a distance, and where this one induces a magnetic dipole on the other. So that's physically what is going on. And so we perform this experiment by altering the time resolved measurement from before by adding a circularly polarized quarter wave plate here, which can change the linear polarized light into a circularly polarized light, either left or right-handed, and also a linear polarizer after the sample, both in the probe path. And the result is, as you see here, so this is the DAS picosecond spectra, this is the DAS nanosecond spectra. The right-handed is this small line here, and the left-handed is the dots, the thicker line. And the difference between these two is a circular dichroic signal. And so you can see that in the picosecond and nanosecond decays, there is evidence of chirality in both. There is evidence of circular dichroism, and this confirms that the bulk CCDW phase in titanium diselenide is in fact chiral. So we expanded on this by doing many measurements, not just at 3 Kelvin. So this is the raw spectra of the fit I just showed you. And recall again that the folded SE4B band is at 690. So this right here is the signature of the charge density wave phase. And you can see that for low fluence measurements, as I go above the transition temperature, this goes away. But it turns out that the fluctuations are also chiral. So this right here is the 620 nanometer line, and this monitors the folded the SE4P band at gamma for the normal lattice. And so this is for low fluence measurements. This is for high fluence measurements. We can see that the melting is happening once again. And yes. So this alters the phase diagram like so. This is the previous experiment where they showed chirality here, whereas the experiments that with circular dichroism show that this whole region has chiral character. Another experiment, now no longer circular dichroism, just the ultrafast measurements, showed that were done with pump probe measurements, and we did experiments at 200 Kelvin and 3 Kelvin, and so this is the decay associate spectra for the different copper doped samples. So it goes from blue to as titanium diselenide pure to red, which is copper of x equals 0.08. So that's ideal superconductivity right here. And this is the progression. And so what I want to call your attention to is that these are all done with the same fluence. This is the 3 Kelvin measurements. These are the 200 Kelvin measurements. If you look at x equals 0.04, this orange curve, there is an instability to optical perturbations of the folded selenium Se4P band. So these are the bands that monitor the CDW bands, and the same is also found in the nanosecond decays as well. So what we did was we took these measurements and we plotted this point as a function of copper doping. So these are both, the blue points are at 3 Kelvin, the red points are at 200 Kelvin, and we see that we see signatures of the quantum phase transition at x equals 0.04. So what's happening here is that on the cusp of incommensuration of the charge density wave, the charge density wave electronic band structure is much more susceptible to optical perturbation. And so that's what's giving us this much larger signal. So these are electronic signatures or optical signatures of this instability at the quantum phase transition. And so we alter the phase diagram like so. The last experiment that I did, or this thesis, was discovering there is a decoupling of the electron-phonon degrees of freedom in the incommensurate CDW part of the TX phase diagram. So what I mean by that is, well, before I get into it, I want to just call out a certain piece of information. This decay right here is from the excited electron interactions with the phonon system. For low fluences, for low pump fluences, the faster this decay is, the higher the electron-phonon coupling. And the reasoning behind that is, if you have more interactions of the electrons and the phonons, they'll decay to equilibrium faster. If you don't have so many interactions, they'll decay slower. So right now, I'm showing you at 600, the Ross transient spectra at 620 nanometers. And so this is monitoring the Se4P band at gamma. Whereas the band at 670, if I'm above the incommensurate CDW and below the incommensurate, so above the incommensurate CDW is in the orange, and below is in the cooler colors, the 3 Kelvin and 6 Kelvin, then you can see that there is clearly a less electron-phonon interaction, a lower electron-phonon coupling in that system. So to conclude, I altered the phase I discovered that there is selenium migration induced at 440 Kelvin for pure titanium diselenide. I showed that there are CDW thermal fluctuations above the phase transition temperature, that the chirality in the bulk CDW phase, that chirality is shown in the bulk CDW phase and in the thermal fluctuations, that there's an incommensurate CDW phase transition, that it coexists with the superconducting phase, and that there are quantum fluctuations of the CDW electronic band, and that there is electron-phonon decoupling in the incommensurate CDW band structure. I would like to acknowledge my professor, Goran Karpetrov, who taught me so much and was with me through all these 4 years. I would like to also thank Alexei Prelev, Joseph Lambert, and many of the other people, some of whom are here today to listen to this talk. I would also like to extend my appreciation to Gary, Richard, and Dave at Argonne National Labs, who helped me do most of these measurements, and also Jeffrey Lin and his group at CERN, not at CERN. I do that every time I see this. At the Center for Neutron Scattering at NIST. I'd also like to thank the group at Temple University, where I did most of the growth, or did all of the growths for this experiment, and also Kogar and company at Illinois. And this work was funded by the National Science Foundation, and I would also like to thank all of you for coming and listening to this talk. Thank you.
Okay, any questions?
I said I was going to do this after I saw the practice version of this, but this is more of a comment than a question. So I would just like to say, especially for your family's sake, that most graduate students, I think, would be jumping for joy if they answered a single question, and most of us are hoping to hone in and ask a better question than we were given. And I think you answered, who knows how many questions were on your slide there, 6 or so. So I know that you were here basically every weekend the whole time that you've been at this school, but this is the most amount of work I've ever seen in a PhD defense at Drexel. So I think it's just an excellent piece of work. And I guess that makes up for all the suffering I had to do with you talking to me about it for the last many years. So anyway.
Thanks, Josh. Appreciate it.
Anybody else? Yep.
So I'm just curious, like in that one with the neutron bridge, we have the nuclear reactor. Like I don't know how Walter was set up, but like how did they get it on a certain point? What, I'm assuming that's a very tiny lattice. Is there just like a beam coming out?
So-
and like moving it? Like,
There are funny stories about that. There at Oak Ridge, there's another neutron scattering facility. They literally just have a hole in the wall where a neutron beam is coming through. It's not like that where I was, but the sample that was the measurement was done on was a centimeter by a couple millimeters, maybe even less than 2 millimeters, and that's a 2 gram crystal, and that's all of that apparatus was focused on that one little point, and so that's what the experiment was like.
Research reactors are not as big as 3 Mile Island.
Just sounds like kind of like a chip on the side. It's like a
Well, if there are no... Oh, go back to Alexis.
Just to fill out. You were talking about this beautiful experiment with selenium diffusion through the crystal, like selenium stability, which is, was partially stimulated by light. And there was extrapolation, right?
Yes.
And you said that if you extrapolate, you will see what? On the end of the curve.
So that was with no light being used.
So there was intensity, right? Or wavelength you were extrapolating?
So the vertical axis was the beam power.
Power.
Yeah, and so that was the power. That's what I was adjusting. And the horizontal axis was the temperature at which I saw the first threshold of that peak starting to form in the Raman spectra.
Right, and based on that experiment, can you tell if the mechanism of it's a photostimulation or photoheating, so it's a thermal effect, as opposed to photo?
If one of the, I didn't quite talk about it, but so that plot.
You said like
yeah.
Photoheating. That's why I'm not.
Right. So that line was linear. So one of the indications is that the line was linear with temperature, and so if it wasn't linear with temperature, then you could make a case that it wasn't associated with the heating. It's associated with some optical excitation. But since it was linear, that's one of the indications.
Thank you.
Yeah.
I'm an astrophysicist, so none work I do any practice. So these very interesting quantum properties of this material, do they have applications for solid-state devices that are of interest?
Yes. So, for example, the chiral symmetry breaking. There is domains that form on the surface that are either left-handed or right-handed in chirality, and so you can imagine that those could be zeros or ones, where you could store information. So you could use it as a storage of information device, for example. That's one way. Another way, like people do this a lot, because you have phase transitions. You have what happens there is a very sudden change of property with a small change in, say, temperature or some other property. And so if you have a detector, for example, and you want to detect light, so light hits it, it heats something up, and all of a sudden you cross the phase transition, you change the properties of the material, and that can be measured. And that's another way that you can use these materials.
There is nothing else. I would request the general audience to kindly exit from here so that we can